This will be delivered by none other than one of the ASEP directors, Engineer Rodolfo Chua, the current business group leader of Structures Design and Engineering Group in GHD Pty Limited Philippines. He has 40 plus years or 15 plus years of experience in architectural building, industrial and infrastructure projects. He successfully delivered complex and large-scale projects that include skyscrapers in New York City, award-winning steel structures, international airport terminals, luxury apartment buildings, world-class stadiums, and heavy industrial plants. He holds a master's degree in structural engineering and an active regular member of the Association of Structural Engineers of the Philippines. Since 2018, he has been actively participating as a resource speaker in ASEP conferences and PIC convention. He is also a current member of the Steel Code Committee for the upcoming 8th edition of National Structural Code of the Philippines and the CPT Committee of ASEP. Now, later part today, this NSCP 8th edition and the sum page will be delivered by none other than our past president, Brother Ariel Santos. May we call, without much further ado, may we call on Engineer Chua.
Maayong buntag kaninyong tanan. Mas mahaba pa ata yung introduction mo, kuya, kaysa i-represent ko this morning. We were only given 15 minutes to present a topic that we did for, the study that we did for a couple of months. So we're gonna do our best to, deliver it within the time limit. So hindi na ako magpapaligoy-ligoy pa. Earthquakes don't hurt people, but buildings not adequately designed to resist the seismic effects do. And since the beginning of the 21st century, 2001, the Philippines suffered over 20 destructive earthquakes causing thousands of injuries and claiming a couple of hundred Filipino lives. That knowing that our exposure to seismic hazards is very high, we have to understand how buildings are designed to resist ground shaking effects of the earthquakes. With that, we're going to present a study that we did, although it's still in the prelim stage, about the comparison of seismic code hazard levels. 15 minutes lang binigay, so we're just gonna focus on the hazard level. And seismic assessment of a new steel SMF building designed according to some PH and the proposed upcoming new NSCP code provisions. Let me start with this relationship between performance levels of typical buildings like condominiums or residential buildings versus the seismic intensity of the earthquake, starting with the frequent earthquakes in which the intent of the building code or the NSCP code is for buildings to remain operational. So meaning you don't have to evacuate the building. And then the second level is what we call the occasional earthquakes, in which the intent of the code is for buildings to be occupied immediately. So this is the type of earthquakes where you have to evacuate, but you can just go back after the earthquake. And then we have the rare earthquakes, in which the intent is to prevent serious injury or life loss. So ito yung sinasabi na life safety intent of the code. And then lastly, we have the very rare earthquakes in which the intention or the intent of the code is to prevent partial or total building collapse. However, one of the misconceptions about the code is that if you design a new building, according to the latest provisions of the code, it's essentially earthquake-proof. Yan yung parating sinasabi ng mga developers and our clients. But that is not true. Because, in fact, in 2010 version of ASCE 7, the American standard that we are gonna follow in the upcoming code edition of NSCP, it explicitly specifies an acceptance of 10% collapse probability under a maximum considered earthquake. So that's our motivation in doing this study. Now, the design of steel buildings is regulated by a series of standards starting with NSCP or ASCE, which sets the basic design criteria and associated lateral drift. And with the publication of some PH, as mentioned by Kuya Cesar, by PBOX in 2021, ASEP will be revising the seismical provisions of NSCP from UBC 97 to ASCE 705, but with some modifications because 705 is quite an old version of ASCE. So we adopted some modifications in the latest ASCE standards. And here, we're going to present the design and evaluation of 3 archetype steel buildings. We have the 4, 8, and 12-story building with architectural layout based on a typical residential building designed to resist 4 seismic hazard levels from NSCP, SAM-PH, and site-specific MCE and MCER. The typical building plan is rectangular with overall plan dimension of 56 by 13.5 meters, and the gravity system is composed of a composite metal deck supported by wide flange I-beams and columns. And as you can see on the screen, the seismic force resisting system is composed of a centrally braced frame along the Y or transverse direction, and we have the special moment frames along the longitudinal direction or the X direction. But for the interest of time, we will only cover the SMFs in this presentation. The seismic hazards are developed from an undisclosed location in Metro Manila, which is approximately 10 kilometers away from the West Valley Fault in Marikina. It can be observed, if you look at the response spectra in the screen, that the ground motion using some pH is significantly lower than the current NSCP values. Now, this unique case in Metro Manila is somewhat similar to the coastal California, but it's the other way around because in California, the probabilistic was way higher than the deterministic. That's why they capped the probabilistic. But in our case in Metro Manila, the probabilistic some pH is way lower than the deterministic current NSCP. Now, this significant difference could be alarming because millions of people living in Metro Manila will be affected if a major earthquake happens that is similar to the great East Japan Tohoku earthquake, if you're familiar with that one. That was 10 times stronger than anticipated by the scientists. And it may happen in our country. Now, during large seismic events, SMFs are expected to develop significant inelastic deformation, mostly, if you follow the code, in the beam plastic hinge location. So it should develop hinging on the beam and not on the column, except for the base. Now, the SMFs in our study are proportioned using equivalent lateral force procedure, just to simplify. And for consistency of material design specs, we just followed the 2010 edition of AISC 360 and 341. Now, for our design, since this is SMF, as we all know, it's controlled by drift requirement, although we use the period from the dynamic analysis and we also follow the exemption on the minimum base shear, but still drift governed. And in the design, the stability analysis, like the large P delta effects, are evaluated by using AISC 360 direct analysis method, and then we model the rigid zones. We ignored the rigid zones, and we consider reduced stiffness. It's mainly to justify the use of K factor equal to 1 for all the steel members instead of calculating all the K values. And then to account for small P delta effects, the amplified first order analysis is performed by using the B1 factors. So it's mainly to simplify the analysis and the design. And also we considered notional loads to account for geometric imperfections of the steel buildings, like out of plumbness. Now, as expected, the resulting design-based shear using some pH is significantly lower than the current NACP 2015. That's roughly 30 to 40% lower for all the building heights we considered here. Looking at it commercially, developers and our clients, there could be big savings in constructing new buildings if you follow the upcoming some pH as it is. But on the other hand, there could be potential issues of damage or even collapse whenever a seismic intensity larger than the estimated anticipated level will occur in Metro Manila. Now, since the intent of the code is to prevent partial and total collapse during very rare earthquake, a seismic performance of SMFs we designed here is evaluated using ASCE 41. Now, the nonlinear force deformation models of the SMF we consider are constructed in accordance with the generalized force deformation curve of ASCE 41. And then the column bases are modeled as fixed, and 3 types of nonlinear hinges are built into the model. We have the beam moment hinges near the face of the column, and we have the moment axial interaction hinges at the column ends, and we have the panel zone hinges. Now, modeling of the moment connection stiffness is required by ASCE 41, but since we use pre-qualified SMF connections, we just assume that the formation of the plastic hinges will occur within the beam and not on the connection face on the column flange. So to further discuss our study, I'm going to give to you to my colleague, Gerard Noval.
Thank you, Sir Chow, and good morning to everyone. So I'm going to discuss about our pushover model and the pushover curve, and lastly, the frame deformation which led to the collapse. It's also assigned the same hinge property at a distance d/2 from the face of the fixed support. Also, all panel zone locations have been assigned a rigid zone up to the face of the column. Drop in the strength in the column and panel zone hinges, as you can see, is caused by the beam rupture shown in the center figure. So all of the 3 hinges, the governing or the collapse hinge is a beam for the 12-story building. So next would be the result of our analysis, which is the pushover curve for the 4-story, 8-story, and 12-story frame. So the pushover curves for all structures are shown. So the idealized bilinear force deformation curve for the collapse prevention SPL is shown in the thick orange line. And locations of the first beam hinge shown in green triangle, and the first column hinge, except for the base, shown in the red diamond. So this developed within the structure. So the collapse mechanism shown in red asterisk, as you can see in the far right of each curve, are also shown, which will be discussed in the next slide. So for the 3 structures, beam hinging developed before column hinges. As you can see that the green triangle are plotted before the red diamond. So however, column hinging appeared for the 4 and 8-story before the structure achieved the target displacement. So the target displacement is marked a red hidden line. So as you can see, the red diamond is before the red line in the graph. So for the 12-story, column hinges emerge within the target displacement range. So as you can see in the 3rd graph. So with the noted observations, the prescriptive intent of the code for beam mechanism is given focus. No column hinges should develop for the structure to behave ideally as per the code. But as observed and realistically, this is very difficult to achieve. So for this slide, the structures are pushed further beyond their respective collapse prevention target displacement to get an idea of their behavior leading to component rupture or collapse. So shown, we have tagged the demand capacity ratio of each component for each structure. So for the 4-story, a story mechanism exhibited at the ground floor to 2nd floor columns. So hinge rupture at both ends of the column developed, causing the structures loss of strength and stiffness. So as you can see in the previous slide, the pushover curve of the 4-story has a steady drop, as you can see in the red dot in the picture. So hence noted by the drastic drop in the strength and stiffness in the pushover curve as shown in the previous slide. So the 12-story structure is unique because comparing it from the two previous structures, it showed the most ideal behavior for collapse. So the beam rupture at second floor caused the analysis to stop before column base hinge reach its rupture point, unlike the two other structures. So for this study, it has been noted that the pushover curve is, For this study, it has been noted that the pushover curve is sensitive to the beam hinge distance, SH. So for future studies, it is recommended to evaluate sensitivity of the beam hinge locations and include the beam column connection nonlinear properties. It is also recommended to try a different approach in modeling the column base hinge, such as pin base with foundation flexibility and modeling of base plate hinge backbone curve. So I will give the mic back to Sir Chow for our.
I think here are the key takeaways. Number one, the seismic demands in some PH is significantly lower than the current NACP provisions in Metro Manila, although commercially speaking, there is potential savings, but again, there could be consequences. And number two, although strong column weak beam in our study, which is the intent of the code, was substantiated, the weak story mechanisms was observed. And number three, the hinging of the column base controls the overall assessment, which is more detrimental than the overall performance of the structures. And lastly, we recommend to have further research to evaluate the sensitivity of the beam hinge location, the column hinge modeling that we implemented, and the implementing nonlinear dynamic procedure according to ASC 41, and probably incremental dynamic analysis of FEMA P 695. Og diha na lang taman, daghang salamat sa inyong